So here we are going to be solving problem 23.29, which says that a uniformly charged straight filament, so that's in red, has a length of 7 meters and a total positive charge of 2.00 microcoulombs. An uncharged cardboard cylinder with a length here of 0.02 meters and a radius of 0.1 meters has a filament going straight through its axis like this. Now we are asked to use reasonable approximation to find the electric field at the surface of the cylinder and the total electric flux through the cylinder. Okay, so the key word here is reasonable approximation. And if we look at the situation here, our cylinder is so small, so here is 0.02 meters in comparison to the filament of 7 meters. So we can use the equation for the electric field of an infinite line. If you don't know how to get this equation, you can go to example 23.7, which explains it in detail. So then all we have to do is figure out what lambda is, and we know that's Q over L. And we know that Q is equal to 2.00 microcoulombs. So 2.00 times 10 to the minus 6 coulombs divided by L, the length of our wire, is 7 meters. That gives us a lambda value of 2.86 times 10 to the negative 7 coulombs per meter. All right, so this is our lambda, and we can just plug that in. So we want to know the electric field at the surface here of our cylinder. So that means that every point along the surface is 0.1 meters away from our filament, right? So our little r in this equation is going to be 0.1 meters. We plug that in and we get 2 times Ke, where Ke is just our Coulomb's constant. And you definitely should be writing out your units whenever you do these equations too. Times lambda, which we know is 2.86 times 10 to the negative 7 coulombs per meter. All of that divided by little r here, which is 0.1 meters. Okay, so that's our equation, plugged everything in. If we do the math, we get 51.4 kilonewtons per coulombs. So that's our electric field at the surface. And we can tell that if this is positively charged, right? So if we have this positively charged little filament here, then that means at our surface, we are going to get an electric field pointing radially outwards. So if I were to take a little cross section of this problem, I essentially have this where I have positive charges on the inside, and then at my surface, I have an electric field that is pointing radially outwards like this. Okay, so that is it for A, and now we have to move on to B that asks us to figure out what is the flux through the cylinder. The first thing we have to realize is that there is going to be no flux going through the pink surface or the green surface, the back surface. And that is because our electric field is going radially outwards. So our electric field is going to be flush. It's just going to, for instance, let's say I have, this is the surface. Well, the electric field's going like this. So nothing is going through these surfaces. And that's the whole thing about flux, is something has to be going through a surface for there to be flux. All right, so that means I'm only going to have an electric flux going through the blue surface here, right? So this blue one. So I have to figure out first what its surface area is so that I can plug that into Gauss's law. And if we remember, flux is equal to the surface integral of E dot dA. Where here, because again the situation is such that we are going to have our electric field going radially outwards, and we know that along the surface, so along this blue here, my dAs are also going to be going radially outwards, because in essence these are just like a whole bunch of like little loops stuck right beside each other, right, to create our cylinder. So dA and E are going to be in the same direction, which means that the angle between them is going to be equal to 0 degrees, right? And that means the cosine of 0 is equal to 1. So that means that we can rewrite this as surface integral of E times dA. Now we know that the electric field is also going to be constant at every point along our surface because we know that our electric field, right, comes from this wire that has charge uniformly distributed around it. So if I were to pick really any point here, and I were to say, okay, what's the electric field like for this little area, and then I pick an area the same size here, we have the same amount of electric field lines coming out of this as we do here. Okay, so because the electric field is constant, we can pull that out, and then we get the flux is equal to E, surface integral, and dA, and this just means surface area. And what is the surface area of our blue here? Well, we know that that is just going to be equal to 2 times pi times r times L, right? So we have the surface area across this blue is equal to that. So then we plug that into our flux equation and we get E times 2 pi r L, where in this case L, well, I shouldn't really call it L because I'm talking about this, I'm talking about the length, but remember we used L down here, so I can call that A if I want to, because it's just the length of our cylinder. Doesn't matter, whatever you want to call it, as long as you know what you're talking about, you should be okay. So that's going to be equal to E, and we've already calculated E to be 51.4 kilonewtons per Kelvin. Kilonewtons per Kelvin times 2 times pi times, and as you've noticed, I have messed up this equation because it's R times A, and this is going to be R, the radius, which up here we know is 0.1 meters. 0.1 meters times 0.02 meters. Right, and then we plug everything in and we get about 646 Newton meters squared per coulomb as our final answer. So I just want to quickly recap the problem where we have an approximately infinitely long filament, right? And we're able to figure out what the electric field is due to that filament at any point R, because here little r is just our radius of our cylinder. So we want to know what's the electric field at any point along the surface here. So that gives us the electric field at any point here. And once we were able to figure out what the electric field was, we were able to use Gauss's law to then be able to calculate the flux that is going through our cylinder. And because we know that the flux is only non-zero through the blue part of the cylinder, we just need to figure out what the surface area of the blue is, which we know to be, this is A, 2 times pi times r times A. And that's the surface area. And that's all we had here. Plug all the numbers in, and that's what you get.